Hey guys, in this video, let's discuss briefly the notion of operators within the C programming language. So overall, just as in mathematics, an operator is a symbol that denotes some set of operations. Now, also just as in mathematics, the set of operations relating to some operator will ultimately involve some amount of entities, and each of these such entities will generally be referred to as an operand. Now within C, it's important to note that the type of an operand, which will be interpreted by the compiler, will ultimately dictate which kind of machine instructions will be generated to perform the relevant operations. And we're going to try to highlight this fact below in a couple of examples, but realistically there are many cases to consider in general, and we're not going to try to encompass all of those here, so please refer to the C language standard whenever more details regarding this are necessary. Now overall, the C language will actually provide access to many operators, and we'll try to cover some of the most important ones for the purposes of this course below, but it will not yet make sense to discuss certain operators, and others will just be omitted entirely for simplicity. Now, another last point I want to mention in general is that in C, just as in typical arithmetic, there exists some kind of hierarchical precedence for the evaluation of operations specified by operators. But just as regarding the types that we said above for operands and how they're handled, this exact hierarchy is pretty involved and will not be described completely in general here. So again, please refer to the C language standard for more details. The only thing I will want to mention about this hierarchy is that whenever it's questionable what the precedence is for some evaluation, you can actually utilize left and right parentheses around any expression, and that will cause that expression to be evaluated before any other pre-existing precedence. So parentheses, just as in mathematics, can be kind of used to force an order of operations, which will be useful in some cases, as we'll see. So for the remainder of this video, let's start discussing and some operators and some concepts regarding them. And for each of the operators we're going to discuss, I'm going to sometimes use the following variables as operands, but whenever I don't utilize these variables, constant literals such as numeric constants, 2, 3, etc. are going to be utilized as operands instead. So the first, I'm going to try to group operators into different kinds of types to make a more sensical and in terms of organization. But the first operator that doesn't really have a good, at least in my mind, can't really be organized with the other groups that I've created is the basic assignment operator. And we've already seen the basic assignment operator. It's just the equals symbol. And basically the basic assignment operator is just meant to alert the compiler to assign some set of memory locations with a certain value. So for instance, the variables that I defined above, where var0 is unsigned 8-bit, var1 signed 8-bit, var2 unsigned 16-bit, var3 floating point variable, var4 an unsigned 8-bit, and var5 signed 16-bit again. I assigned some random values, some again particular instances of values to those variables and those memory locations. And I just want to show throughout this video how the compiler actually can interpret such C code. So let's go ahead and run this, start debugging this code, and then we can view the disassembly to see what kind of assembly was generated for this. Again, we have no optimization on right now. Just trying to move this. I guess I won't try to, it's giving me a little pain right now. Okay, so disassembly is already up, but if you don't see this, I've mentioned before, I believe, debug, Windows, disassembly, and also there's this button right here for disassembly if you have the standard view. So this breakpoint here, var0 equals ff, all the assembly code that's generated, which again, different assembly code could be generated in different contexts, but this is a valid means for doing so. It sets some temporary register R24 to be ff with ser instruction, and then it stores using the y pointer plus an offset of 1 the value of R24. And you can actually figure out I'll hover over and pause over, you can pause over these portions of the assembly code, and you can try to figure out how exactly y plus 1 corresponds to var0. But by default, one thing that's useful to mention is generally the memory will be in reference to the stack for most variables if we don't specify certain other type qualifiers or certain criteria for the variables. I'm not going to go into too many details on that right now, but in this case, that's exactly what happens with this memory. And we're going to see right here, it just popped up internal SRAM using near the stack pointer, or this is the stack pointer was referenced, it stored that memory in relation to the stack. And so again, not going to really focus on that too much, but just wanted to show that there are certain ways of storing these variables. So for instance, again, 16 bits utilizes 2 memory locations, floating point, which is ultimately in our context going to utilize 32 bits of memory, and the IEEE 754 format by default. It will utilize certain values, which I'm not going to go into, but just throwing out keywords if you guys want to explore on your own. So that's all I wanted to really show for the basic assignment operator. And then continuing on, we're going to get to the next section that I classify as arithmetic operators. And arithmetic operators are basically just used as to provide access to standard arithmetic functions that we're accustomed to from basic math. So I'm going to kind of fly through most of these, but show a couple key points. So the first one may be standard is addition, which again utilized by the standard plus operator. So the key thing that I want to highlight here for the first time in a couple places on later on is that we need to recognize that the compiler again is interpreting our C code and is going to generate some form of assembly code for our target microcontroller or our target device. So the question is, for each of the following lines of code, where this line of code is just calculating 2 plus 3, the next is taking 3 plus 2 and storing that result with the basic assignment operator we've already mentioned into var0, that memory location, and then doing var0, whatever's in that memory location at the time, which would be 3 plus 2 or 5, and then adding 3 to that, storing it back into var0, and then adding 2 to that, storing it to var2, so on and so forth. How are these operations interpreted? Well, that all depends on the operands and ultimately also on the, if we're using assignment, on the result or on the memory locations associated with the place that we're storing that data. So I want to mention that the first statement really is kind of nonsensical in terms of creating assembly instructions, because 2 plus 3, it's not actually utilizing that data. So most of the time a compiler, if it's smart, even without optimization, will realize, hey, I'm not, this is not going to be utilized at all, so I'm not going to even perform this in terms of assembly instructions. But I just included it here because I wanted to highlight just the first statement using simply the addition operator and not confuse you with the assignment operator as well. Now, it's important to note that constant literal operands, it's all compiler dependent how these operands will be interpreted. By default, I believe the C language standard specifies that these, if they can be represented with the type int, which in our case is with the avr-gcc compiler tool that we utilize within Atmel Studio by default. These will be interpreted, that type int is 16 bits or 2 bytes, which can be a problem, but in this case, again, not going to be utilized probably here. Now, still though, the compiler can sometimes be even intelligent without optimization. So in this first line, we're going to see, I believe, that when it stores 3 plus 2, it doesn't actually do 16-bit addition because it recognizes var0 is an 8-bit unsigned value, or ultimately should be stored within an 8-bit unsigned value. So if we continue to that, and I go back to disassembly, we see that some example assembly code generated is just literally loading the value 5 and storing that into the memory location associated with the y index plus 1, which I'll just tell you again corresponds to this FF here in this memory window, but it corresponds to var0 ultimately. You can just take my word for it. But the interesting thing to note here, first of all, is that there actually is no addition operator that happened. So, addition operation. So what's interesting to note is that in this case, the compiler, even without optimization, recognizes, hey, there's no need to actually perform this addition using hardware. Let's just recognize, hey, 3 plus 2 is always going to be 5. So let's just use the constant 5. And this is still some form of optimization, even though optimization tool is quote unquote turned off or to be none, but still some basic optimizations will be performed by the compiler that we cannot prevent. So that's interesting here. The next thing was var0 plus 3 stored into var0. Here we actually load from that var0 location into some register. And then to do this plus 3, since we don't have in our microcontroller architecture, we don't have an add immediate instruction. We have an add immediate word, but no 8-bit add immediate. So but we do have a subtract immediate. So if we actually subtract immediate using a 2's complement format of -3, so subtracting -3, as we know, ends up being the same thing as adding 3. So this ultimately ends up adding 3 to whatever was stored within var0, and then we store that back to var0. So that's interesting too. Now var2, we actually now get to, var2 is a 16-bit unsigned variable, so we defined it to be as. And now we're taking an 8-bit value within var0, adding 2 to it. So how does our compiler generate code for this? Well, loads var0, then it moves for some reason, which this is kind of a nonsensical instruction that's kind of just a artifact of the no optimization that we have. It removes R24 into R24, which I don't believe there's any reason for that, but I may be incorrect in saying that. And loads 0 into R25, and then it adds immediate word R24, which this syntax actually is the same thing as add immediate word R24, R25, because it's going to add a word, or it's going to add some immediate value to a word of memory, which is, in this case, the word is going to be stored within registers R24 and R25. Again, please refer to the instruction set if you're confused about any of this. And then it's going to add 2 to that word of R24 and R25. And in this case, that's adding this offset of 2. And you can see that if it's using R24 and R25, where R25 is actually going to be the uppermost bit of that word, uppermost byte of that word, then 2 is still being added to the lowermost bit, and the uppermost, or sorry, byte again, and the uppermost byte is just set to zeros. So var0 basically just gets sign extended with the zeros, and then 2 is added to that, and then that result is stored back into y plus the memory locations associated with y plus 3 and y plus 4, which you can trust again correspond to variable 2 or var2. So again, interesting to see how the compiler actually performs this kind of addition. Now the nice thing is, in general, we're not going to worry too much about how the assembly code's generated, but I'm trying to highlight here in these first few videos within our tutorial series how the compiler actually translates this abstract language or set of operations specified in C code to some other lower level form of code that can be handled by our microcontroller. Now the next set of operators besides these guys were, and let me skip ahead to this, okay, were subtraction. And I'm not going to spend too much time on this, but you can, the subtraction very similarly handled as addition, just with different operations, and sometimes 2's complement depending on the specific values. So in this case, subtraction again specified by the common minus sign that we're used to in math. Not going to really spend too much time on that at all. Next guy is the unary minus, where unary just basically means that there's only one operand. Above, we've had these operands we showed so far have had 2 operands on the left and right hand sides. Unary just means that you're going to have one operand. So in this case, 2's complement is going to be, unary minus is just going to take the 2's complement form of some value. And again, in this case, when we don't actually utilize the result of some operation, it's a useless result, and the compiler will probably optimize it the way it should. So I wanted to highlight, if we actually stored something like this to var1, here we would store a constant, because again, the compiler can see there's no operations that actually need to be performed. It can just load a constant value. But here in this second operation, that's where it's actually going to perform the 2's complement. So let's see that really quick. Oops, I went to the wrong. I want to go to disassembly. Here it actually loads into R24 from y plus 1, again, var0, and then it does negate R24, which ultimately is a 2's complement, that takes the 2's complement. This is, again, an instruction provided by AVR, and then it stores that back into, memory location y plus 2, associated with y plus 2, which is var1. So again, just seeing how this corresponds to assembly instructions. We have multiplication besides subtraction, uses the asterisk symbol. Not going to spend more time on that. Division, this one's a little bit tricky sometimes, so I want to spend a second on this at least. So with division, what's important to note with C is that whenever integer division is performed, there is no fractional portion of a result that is stored. So in this first case where I have the division of 3 divided by 2, we know if we are using real valued division that we would get 1.5 as the result. But here with integer value division, especially when we actually store that into a unsigned 8-bit type, which can't represent by default fractional values, that result, the fractional portion actually gets truncated and discarded. So 3 divided by 2 actually ends up being stored as 1 in this case. And again, this is a constant operation, so the compiler will ultimately do that itself and not actually perform a division. And same with this guy, constant operation. But here, var3, we now have a floating point value. And to specify kind of a floating point division to be safe sometimes, one way is actually incorporating a decimal point with one of the operands at least. And usually compilers will then recognize, hey, I need to actually perform a floating point division. And as we're going to see in a second, as I've mentioned previously as well, we want to stick away from floating point operations as much as possible because they actually are very involved in terms of our architecture, because we don't have a floating point unit hardware. So in this case, we would actually get 1.5 as a result, but again, remember that will be stored in some relevant format such as IEEE 754, specified by that standard. So I want to show here the disassembly for if we were to divide an 8-bit value by 2. Now an 8-bit value by 2, whoops, it dragged my thing again. Disassembly, what I want to mention here is that the compiler recognizes, well, divide by 2 we know is the same thing as shifting right by 1. So it actually generates code that does that shift right by 1 instead of using division operation, which usually ends up being a little bit more involved. So whenever we can divide by power of 2, we want to usually shift as much as possible because that ends up being a little bit more efficient generally. So it does a shift operation, stores back into the relevant memory location here. Now, when we have a signed value divided by 2, here it actually does a little bit more involved operations, which I'm not going to go into too much. But the main thing I want to highlight is just this: it performs ultimately also an arithmetic shift to the right. So if you want to focus on this yourself more, maybe pause the video. But here you can recognize, the compiler recognizes a signed value, so let's do an arithmetic shift. Now divide by 3 actually does something interesting. It uses a lot of different instructions, which just for time I'm not going to explain here. I'll let you pause the video and try to figure out yourselves, but just want to show you that a shift right operation is not sufficient in this case. Now lastly, when we get to floating point division, we actually get a very involved situation, very involved set of operations. So I'm just going to kind of scroll through and not at all try to explain this to us, but basically the set of instructions keeps going beyond this, goes all the way down, calls some subroutine, which is automatically implemented down here at B3, which then does, I believe it was B3, yeah, and then does another long set of operations, which you can try to go through on your own, or maybe compile such code yourself. But so this hopefully just shows that in general, floating point operations without a floating point unit can be pretty involved, and we want to stick away from it as much as possible. So that's all I want to show with division, at least. Just recognize again the whole integer division or floating point division by default. The last arithmetic operation I want to mention is the modulo. The modulo is going to be useful in some circumstances, and we're not going to get into those here, but I at least want to mention the operator. It actually performs the integer remainder. So 3 divided by 2 is 1.5, but another way of saying that is that 2 goes into 3 one time with an integer remainder of 1. And this modulo operator, the percent sign in C, returns that integer remainder. So 3 divided by 2 has an integer remainder of 1. So this result will return 1. But recognize that 1 does not mean how many times 2 goes into 3. It's the remainder of how many times 2 goes into 3. So in this case, if I put 2 divided by 2, 2 would go into 2 one time, and there would be a remainder of 0. So in that case, the result would be 0 if I put 2 modulo 2. So again, we're going to see that later on. I just want to show the operator one time. Now, the next set of operators is comparison operators. Now, comparison operators are used to compare two numeric expressions. And there's going to be different ways that these are utilized, but essentially, the functions associated with comparison operators will result in a value of either 0 or 1. And the main intention of these values is where 0 and 1, these values are going to be to represent some Boolean logic value. And where, just as in general, an idea or a notion of false is going to be associated with the value 0, the result 0, and true is going to be associated with the value 1. And we'll see some examples just now below. So the first one probably is the equal to operator that we want to discuss. An equal to will use this double equal sign symbol and utilizes two operands. So if we were to say 3 equal or 2 to 2, this will ultimately perform an operation that checks whether or not 3 is equal to 2. And in this case, since 3 is not equal to 2, you can think that this comparison function should return a value of false, or in the context of Boolean, it will return a value of 0. And likewise, if we were to check 3 against 3, 3 is equal to 3, so that result would be 1. And to actually see let me continue it because I edited that code. If I actually want to see some compiler generated assembly code for something like this, I have to actually do some meaningful instruction assignment probably. So I'm going to check, and here is where I actually use parentheses for the first time. I'm going to check whether or not var0 is equal to var4, the memory within each of those locations, if they're equal, where both of these are unsigned 8-bit values. And then that result, either 0 or 1, I'm going to store in var0. Now, if we were to check above, actually, I don't really care for the purposes of this video. I just want to show us disassembly. Here, it will actually load from var0 into R18. It'll load from var4, you can believe me again, into R25. Then it will compare these two values. And if they're equal, it'll jump to this line of code. And this line of code will store whatever is currently in R24 to var0. And whatever is in R24 right now is actually 1. So if they're equal, it's basically storing that result of 1 like we said. So it's equating to true. Now, if they're not equal, it won't jump or won't branch, and it'll actually set R24 to be 0, which associates with this value of false, and then it will store into var0. So again, there's that idea of storing a true or false value from this comparison function. So that's equal to. Now, not equal to, I'm just gonna kind of fly through the rest of these comparison operators. Not equal to just does the exact opposite, checks whether or not two operands are not equal. So in this case, 3 is not equal to 2, so the result would be 1. Again, compiler optimizes this the way anyway, but the main idea is checking whether or not what not equal does. And then here, 3 not equal to 3, 3 is equal to 3, so the result would be 0. Okay, that's not equal to. Greater than actually just does the same standard mathematical greater than idea. So 3 greater than 2, that is true, so the result would be 1. 3 greater than 3, 3 is not greater than 3, so the result would be 0. And then there's similar operators for less than, greater than or equal to, and less than or equal to, where I've provided the relevant symbols for those. Okay, but I want to try to not spend any more time on comparison operators. The next set is logical operators. Now, logical operators are a little tricky, so we're going to spend a tiny bit more time on them. But logical operators ultimately operate on the implicit logical value of some data. So basically, the compiler there's going to be operations that somehow manipulate some numeric expression, and it's going to figure out whether or not the data or the value of that numeric expression should represent a logical true value or logical false value. And ultimately, logical operators are meant to provide access to Boolean functions, not, and or. So just as I said already, for operations that involve logical operators, the C compiler will generate machine code that interprets logic values from numeric expressions. And usually what this ultimately means is that the generated machine code will simply compare the relevant numeric expression to the value 0, and it will either check whether or not it's equal to 0 or not equal to 0, and we'll see this in a second. Now, what one shortcut kind of remember from here on out is that the C language basically attributes any non-zero numeric value to be true. So basically anything that is not 0, any value that's not 0 will ultimately usually get evaluated as true and will be basically interpreted as the value 1, even if it's not 1 and it's some other non-zero value. And only the value 0 will be considered false generally. And 0 will be that value, associated value. And we'll see this later on more, but logical operators, just as these other operators that we're mentioning now, will be utilized heavily. But logical operators, especially for control-based operations, which we're going to discuss in another video. So the first guy is the logical not operator. So to introduce this guy, it's the, and I didn't specify here, but that would be the exclamation point. And the exclamation point will basically, it'll look at this value in parentheses, and we don't have to do parentheses, but I'm just grouping it a little bit more meaningfully. It'll look at this value, and that value, numeric expression, is non-zero. So 3 will be attributed to the logical value true or 1. So not of 3 is the same thing as not of the true value 1, which we can logically deduce will be ultimately the result 0. So this, any non-zero value gets equated to true, and then the not of true would be false. And similarly, we could do 0 here, and then 0 is be considered false, and the not of that would be considered true, so on and so forth. And I just wanted to show here, actually, in terms of what would be compiled, if I take the logical not of whatever is within var0, what that will ultimately do is just test whether or not var0 is 0, and if it is equal to 0, it will simply store whatever's in R24, which happens to be 1. So basically, if the value within var0 is 0, it will store in this result var0 the value 1, aka it's nodding that value. And then if it isn't equal to 0, it will store the value 0 into var0. So basically, if it's not 0, then it gets counted as the logical value 1, and then we store the not of that, which is 0. So if that's a little confusing, just pause the video and think about it a little bit more. But that's an important note to mention, that any non-zero value will be considered true within the context of logical operators. So that was not. Now, and, the logical and will basically take the operands, equate them to whether or not they're true or false. So any non-zero value true, any 0 value false. So in this case, true and false is the same thing as we know in typical logic, false. And true in this case, where any non-zero value is true, will be considered true. And I don't have any assembly code for that, I guess. So just recognize here some and instruction would most likely be generated. Or exact same thing, any true value, any non-zero value is true, or with any 0 value 0. So we get true, and then so on and so forth. I'm not going to spend any more time on this, but hopefully the point has been driven home. Now that was pretty much all for logical operators, or the ones in C. So the next set is bitwise operators. Now bitwise operators are ultimately meant, unlike logical operators, they're meant to provide access to Boolean logic functions. That's the same, but instead of operating on the overall value implicitly, or the implicit Boolean logic value specified by some numeric expression, bitwise operators operate on the individual bits of the numeric expression. So we'll see what this means in a second, but I just want to mention first that bitwise operators are going to be utilized heavily whenever we want to manipulate or assess what some individual bit of some value is. So think, we already have been doing this in assembly, but when we've been manipulating status flag values or bits within some configuration register, etc., we've been utilizing some form usually of individual bit manipulation using Boolean logic, such as and, or, etc. So the first of such, just as kind of similar order to above, bitwise not doesn't actually take this non-zero value and consider it to be the value 1 or true. It actually performs the 1's complement of each individual bit. So this result will ultimately result in the value 0, 1, 1, 0 in terms of binary. So this actually manipulates individual bits rather than the overall bit. So different than logical operator of not. And then this is the tilde operator, or tilde symbol to represent the bitwise not. In this case, this assembly code would just be something like as the complement instruction, which does the ones complement of some value. Okay, now bitwise and is very similar to the logical and, except now there's one ampersand symbol instead of two ampersand symbols for the logical and. And here again, each bit will be compared to the corresponding bit in the second operand. So in this case, 0 will be ANDed with this 1. This 1 will be ANDed with this 1, and so on and so forth. And the result in this case should be 0, 0, 1, 0 in terms of binary. And then if, again, this would be correspond to some kind of AND operation, which I guess I can look at. Yes, some AND operation. And I think I mentioned above some AND operation for the previous logical AND. I think in my mind, I was just confusing that with bitwise AND for some reason. So in this case, it would do some kind of comparing with 0, not actually an AND operation in general. So let me correct myself from earlier. And bitwise OR, very similar thing, just does the OR operation between two pairs or pairs of corresponding bits of operands. So here, if you pause the video, you should be able to equate the value 0, 1, 1, 0. Okay, now a couple other bitwise operators rather than logical operators. There's XOR, which is the exclusive OR of some operands. And here, I haven't actually explicitly mentioned, but I'm just doing 4-bit values. But again, generally the minimum is going to be 8 bits or more. So I'm just doing for simplicity 4 bits. So exclusive OR. Then there's bitwise left shift, which has this double less than sign symbols for shifting by some value. So if I do this operand and I use this left shift operator and specify a shift amount, it will shift this overall value that many times. So in this case, it will shift 0, 0, 1, 1 twice, which will ultimately result in the value 1, 1, 0, 0. And then similarly, I could shift 3 times this value 1 and get 1, 0, 0, 0. You can think shifts over 1, 2, 3. Okay. Then there's right shift, which I'm not going to go into, but very similar. Just recognize that the compiler, depending on the value or the operand itself, might generate arithmetic or logical shifts. Now, almost to the end of our operators list, compound assignment operators are ultimately meant to simplify just a C statement, and they're meant whenever you're going to do some operation, some certain operation, and then an assignment following that, which we've seen that plenty of times already in this video. So as an example, there's the addition assignment operator, where if I wrote something like var0 plus equals 5, where plus equals is that compound addition assignment, this would ultimately get translated into something like var0 equals var0 plus 5. So some assembly code will generate something like that, which we could see. It does this loading from var0, then it does again, similar as what we've seen earlier on, a 2's complement subtraction, and then it actually stores back into var0. So it combines that into one C statement just to make the C statement a little bit more simple to write sometimes. So there's addition. Another one that's you won't usually see as listed as a compound assignment, but I'm going to consider here as a compound assignment, is the increment by 1 assignment. So ultimately, this double plus sign, if you put before or after a variable, will be ultimately equal to var0, or in this case, it will be var0 equals var0 plus 1. Now, there is, we want to be technically accurate, so let me write out actually, because I didn't list it here already. There's a difference between the following, if I wrote plus plus var0 and var0 plus plus, or some other memory constant or variable. Here, the plus plus following this value or this memory location is called a post increment. And basically, if we were to utilize this in some statement, so let me actually write something like var4 equals var0 plus plus. What would actually happen here is var0, whatever's currently in var0 before this increment by 1 would get stored into var4, and then there would be a post increment to var0. So a post increment, basically, if there's some other manipulation of this data with some other operation, in this case an assignment operation, that happens before this increment by 1, which is useful in some cases. And that's not really pertinent for this discussion too much, but I wanted to let people know so they don't get caught by that as a gotcha later on. Now the complementary, the plus plus before some value is a pre-increment. So if I were to do var4 equals plus plus var0, here the compiler should generate code that actually increments var0 before it stores it into var4. So that's the actual syntax for specifying the order of operations of this increment. And then similar, there's subtraction assignment, compound assignment, where again, minus equals uses the minus and the equals symbol to be equivalent to something like var0 equals var0 minus 5 in this particular instance. There's the decrement by 1 that has the same post-increment, pre-increment notion attached. There's multiplication assignment, the asterisk equal. You can probably start seeing the pattern by now, and because of that, I'm just going to list out the other ones that are the most prevalent. And I believe these are really the only ones available by default. Division assignment, modulo assignment, bitwise and assignment, bitwise or assignment, exclusive or assignment, left shift assignment, and right shift assignment. And very similarly to the above, you can hopefully create your own examples of what these would turn into in terms of an assignment and each of these operations. But I'm going to let you guys do that on your own. And lastly, I just want to mention a couple other operators that don't really fit into their own section besides miscellaneous. The first of such is the conversion or casting operator, which is going to be, you'll see below in a second in an example, the symbol usually have parentheses, and then you'll specify some data type and then some other operator, which we'll see in a second. But ultimately, the conversion or casting operator is going to be used whenever we want to change the type of some underlying data. And that's going to really be used so that the compiler will generate some other form of machine code to manipulate that converted form of data. So for instance, the following, which again, since we're not actually utilizing this result of this operation, is useless, but as a preliminary example, if I were to write parentheses int16 and then the operand var1, where var1 were redefined above is an signed 8-bit value, what this will do is convert that signed 8-bit value into a signed 16-bit value, which will ultimately mean that there's a sign extension of var1. And to see that, let's actually assign -1 to var1 and then assign to var5, which is a signed 16-bit value defined above, the sign extended version of var1. So let me go to that. And if I were to go to disassembly, we actually see that ff is stored into var1 y plus 2. And the sign extension, it's a little interesting how they do this. It loads whatever is in var2 or var1, excuse me, into register R24. Then it moves that value into register R0 as a temporary manipulation register location. And then it left shifts by 1 R0. And ultimately what this is going to do is it's going to check whether or not the uppermost bit is set, because this LSL instruction, if you check the instruction set, when you shift by 1, if the most significant bit was set before that shift, the carry bit of the status register will actually get updated with whatever that most significant bit was. So if the most significant bit of that operand was a 1, in this case meaning that it's going to be a signed value, then the carry bit is also going to be a 1. And the opposite is true as well. It'll be 0 if the most significant bit was 0. And the reason that's important here is that the next instruction is a subtract with carry. So you can try to do this yourself and figure this out, but ultimately it's going to take the value R25, which in this case is, I don't believe I actually remember what R25 is. I guess it's going to just, oh, I see. So basically it doesn't even really matter what's in R25. it's going to subtract R25 by R25, which we know should be 0, but because the subtract with carry instruction also includes the carry bit when it subtracts, so basically we'll subtract including this carry symbol, this carry sign. The result of this will either be 0 or -1, which will ultimately underflow and become FF in 2's complement format. So basically, then this result, it gets utilized as the second byte of data for var5. So to overall repeat, the whatever was currently in var1 gets stored, so R24 gets utilized again as the lower least significant byte of var5, and then this operation to calculate whether or not the most significant byte should be sign extended to be all ones or FF or all zeros, 0, gets performed by this set of operations and then gets stored in the uppermost byte of var5, which is associated with y plus 11. So I can understand this is kind of confusing, but this is again something you pause and look at and ponder about. But this is a very interesting way of going about performing that, checking whether or not it should sign extend with ones or zeros in a kind of a pretty efficient way. So look over that in your own time. So that was one example of casting. There's all sorts of forms of casting that we'll see throughout in general this course in C programming. One other form might be if we wanted to perform some floating point division regarding something that wasn't floating point by default, such as var0 in our case. We could cast var0 to be floating point, and then to be a little bit more explicit, if we want to divide var0 in terms of floating point by 3 in terms of floating point, we'd probably cast both to be float, but that's probably not necessary for most compilers. I just want to be a little bit more explicit here. So this would ultimately translate to performing a floating point operation, or it should. So that was casting. I just want to mention and show that because we'll see that later on. The last miscellaneous guy for this, and overall the last operator for this video, will be size of. Now size of is not going to be utilized by us much in this course at all. I just want to kind of introduce you all to it, and in general it's used, but I want to introduce you all to it so that we don't, if we do see it later on, that you're not all confused by it. Basically what size of does is simply evaluate how many bytes of memory are to be used by some operand. And this is ultimately going to be useful whenever pointer arithmetic is performed, but the actual manner of how we're going to use pointer arithmetic, which we have yet to discuss pointers in C yet, will be not common for our purposes, but again, you all will probably see it in your future if you continue to be programmers in some capacity later on. So it's good to introduce you all to this operator now. So as a simple couple examples of what size of could do, if we were to do size of var0, var0 is of type uint8t, so really only 1 byte of memory is associated with var0, so the result of this operation should give you 1. Similarly, var3, which is of type float, which in our case the compiler utilizes 4 bytes of memory for float types. Size of var3 should translate to 4, representing 4 bytes of memory. We could similarly do size of float. We could explicitly write the type, and in this case, if we were to go there, we would actually see that it immediately loads just the value 4 and stores that into var0, again representing that float uses 4 bytes. And then lastly, interestingly, we could check the size of a constant expression, and here the constant 3 actually gets interpreted as it uses 2 bytes, which is referring to what I mentioned earlier, that constant literals or numeric constants get translated usually to of type int, which in our case our compiler utilizes 2 bytes for type int. And so really these are the only examples of size of I wanted to mention. And this was a pretty long video. I hope that you all stuck around and listened to some of my rambling in some cases, but basically these are the core operators we'll utilize through this course, and hopefully you'll see when we actually utilize them later on, you won't be confused of their usage. So I hope this helped, and in the next video, let's get into some other topic.